Okay, so I'm going to step you through your first lab. We're going to go to the page where we put up the Tinkercad breadboarding, and you're going to use a link that you use to sign up for Tinkercad. If you didn't sign up for Tinkercad, you need to go do that now. Okay. So your screen might not look like mine, but once you sign up and you log in, all you have to do is go up here to this little icon, click it, and you'll be presented with a whole lot of options. Your designs that you've worked on will be over here, but you have options for 3D design, circuits, and code blocks. What we're going to be interested in here is circuits. Okay, so you'll click on circuits, click on create new circuit, and it'll take a minute, but you should be presented with a work area and a components list. If you look through here, you'll be able to see everything that they have, and we can do a lot with the components that they have right now. Okay, we'll start with something simple. Make sure that we all get on board about how we're going to wire this. So make sure it's on basic components, and we're going to go look for a breadboard. Okay, so we'll grab that breadboard or click it, and it'll pop up over here. Okay, now a breadboard is a neat way that we can prototype circuits without having to break out the soldering iron. So when we solder something, it's really hard to take apart, and if we make a mistake, it can get messy pretty quick. So a lot of times when you're working with the circuit, the first thing you're going to do is use a breadboard. A breadboard isn't very hard to understand. All that's going on is there's a little spring in each one of these rows that when you stick a metal component in it, and then stick a metal component in a different hole in the same row, you'll get an electrical connection. And so let's say row 1 right here. Whenever I hover over it, all of the holes on row 1 light up. That's showing you that they have an electrical connection. So anything I put in this hole right here will be electrically connected to anything that I put in any one of these 4 holes here. Okay, so we've got vertical columns here, and we've got horizontal rows here. Now if you notice, like this long row right here, they're all connected, and there's a little red plus sign. The plus and negative sign don't really dictate what you plug in there. They're just there so that we can keep track of where things are. So it's good practice that we're going to put our positive supply on the positive rail and our negative on the negative rail. That'll save you a lot of problems in the long run. But sometimes we only need one power rail, and we can use the other 2 down here for something else. Now notice that whenever I click this negative power rail, this one's not showing up. Right now they're not electrically connected. So this row right here, anything I put in any of these holes are going to be electrically connected. Anything I put in this positive rail will be electrically connected. If we want this rail to be connected to this rail, we'll have to put a jumper in. All a jumper is a piece of wire. Okay, so hopefully we've got what's going on with the breadboard. It'll make more sense as you use it. So we're going to drag a 9-volt battery in here, but it's not really where we want it, position wise. So we'll go over here to this rotate clockwise component button, and we'll rotate it until we get it to something that we like. That looks pretty good. Okay, so what we're going to do is we're going to connect the negative terminal And if you hover over a point, it's going to tell you something about that point usually. So we've got negative terminal right here, and something about 9-volt battery. The big terminal is actually the negative, and the big slot in an outlet is our neutral. The little terminal right here is positive. So what we'll do is we'll click on that negative terminal, and we'll drag it over here to this negative rail. All right, we could leave this. We'll click, drag, and then click on a hole that we want to put it in. In the real world, this would be a wire that we actually stick in a hole. Now, green means a lot of things, usually ground for us, but we want to keep things kind of simple and easy to follow. So we're going to click on this. Every time that we make a wire, it's going to give us a little opportunity to decide what color wire we want it to be. Okay, so now my green, or my negative row right here is connected to the negative terminal of the battery. I want to stretch out the positive wire, click on a hole, let's change it to red. Alright, now the reason these rails have so many is because there's a lot of things that require power. And so maybe a transistor is connected to 3 things, or maybe 2 or 3 things. But the battery is usually connected to a whole lot in a circuit, so they make these long rows so that we can better route that power. Well, just so that we're good when we get going with a bigger circuit and we might need more power rails, let's go ahead and connect this negative hole row to that negative row. Let's make it black so we can follow it better. And then we're going to connect this positive to this positive. We're going to make that red. Alright, now anything we plug in this row or this row will have power from the battery's positive terminal. Anything we connect from this row or this row will be connected to the negative terminal. Okay, so now let's put a button in here. Okay, so we're going to put a button somewhere here. Now notice this little track right here. Like in between those rows, there's a lot of components. Like if we look down here, we'll see what's called a dual inline package. It might be under, bigger or the all components. So a lot of chips are made so that there's legs on both sides. Well, if you've got a leg here and a leg here, and a row goes all the way across them, you're going to short those legs. So we have this little channel right here on the breadboard that helps prevent that. So this row right here, 22, is not connected to this row right here, 22. Okay? If we want those connected, we're going to have to put a jumper across them. So what that does is that makes it so that we can plug in something like this 555 timer, and power needs to go to this pin. We'll learn how to do that later. And ground needs to go to here. If this row was connected to this row, those 2 pins would be shorted. There's a whole lot of electronics in a DIP, a DIP package, dual inline package. So you're going to have to get used to that. This pin right here is usually not connected to this pin, but it's a very efficient form factor for circuitry. Okay, so what we're going to do is we're going to delete that component. But right here we've got a terminal 1B, terminal 2B, terminal 1A, terminal 2A. Now, it might be confusing which ones connect to which. In the real world, I would just put a meter there and test continuity. Test it, push a button, test it, and see which ones make connection when you push a button. Alright, so we're going to connect whatever's on this terminal to the positive rail right here. So any of these holes would work. I like to put it as close to the rail as possible so that I have more room later. Let's say that I put this wire right here, then that gets in the way of all these other holes that I could jump off of if needed. And it makes it look cleaner. And a cleaner circuit is easier to troubleshoot and follow. Okay. So I'm going to go and hook this up there. Right click it. I don't know why it's not giving me a choice for colors. Oh well. I kind of would like you to change the colors as needed. I'll figure out what the bug is in a minute, so I'm not going to count off on there unless we find the bug before this is over. Okay, I'll show you how to change that. Alright, so we're going to have power to this, and then the button's going to stop the power. We've got a contact that's not connected, and when we push that button, it will. So anything we come off of this will turn on whenever we push that button. Alright, so one of the first components that we're going to learn about is called a diode. If you look right here, we've got two different diodes. We've got a diode and a Zener diode. We've got one more component that's a lot easier to understand, and that's called a light emitting diode. Okay, commonly referred to as an LED. Okay, so we're going to put this LED here, and we'll keep it red. We'll hover over this anode, this cathode. We'll talk about how to recognize those in the real world, but right now we've got something telling us that that's what they are. Now with diodes, current can only flow in one direction. We need it to flow from the anode to the cathode when we're talking about positive and then negative. We'll talk about electron flow later. So what we need is the anode to be connected closer to the positive end of the power supply and the cathode to be connected closer to the negative. Okay, so what we're going to do is we'll rotate this, okay, so that the anode is going to be closer to this button, which is closer to the positive. It doesn't really matter what holes you put it in, as long as it's two separate holes that aren't connected to something that shouldn't be. But this will make wiring easier instead of having wires cross over each other. Okay, so what we're going to do is we're going to go in and we're going to connect that hole to that hole. Okay, so this came back. We're going to make everything on the positive side of the LED red. Everything on the negative side of the LED black. Okay, so let's see if we can't get... Well, I could have changed it there, couldn't I? Alright, so we're going to go in and make sure this one's red. Alright, so follow from the 9 volt, go into this hole. So I'm going to go all the way across here, go out of this hole, back up to this rail, all the way to this hole, across to this row. It's going to stop at this contact until we push it. And then it's going to go out this terminal, into this row, out this hole, into this hole, across this row, into this anode, and then nothing. If we don't make a complete circuit, we don't have current flow. So all those electrons that will be building up on the negative terminal of the battery aren't going to move unless they have somewhere to go. Okay, so to make this circuit work, we're going to take this cathode. We're going to run it over here to a free little area, and I'll show you why in a minute. We could take a wire and just connect it directly down to here, but it's going to make for a messy circuit and it's going to be hard to follow. So what we're going to do is we're going to go from there to there, and then that's going to give us these nice, right angles that's going to help us follow what's going on. Now, whenever I turn this on, I'm going to go up to start simulation. I'm going to push that button. And what we're going to do is we're going to blow an LED. Okay? Now, in the real world, when you blow an LED, sometimes it's like a firecracker. It depends on how much current you put through it. It won't hurt you unless you're not wearing proper safety gear. Every time you deal with electronics or electrical stuff, wear safety glasses. Okay? So, it might bounce off of you, but if it bounces into your eye, you're going to have a bad time. Okay? So, wear safety glasses. Now, I'll show you why in a minute, but we're going to start the simulation, and it immediately blew. And when we hover over that little explosion, it says current through the LED is 915 milliamps, while absolute maximum is 20 milliamps. You got to realize that even though an LED might look huge, like the actual stuff that's going on is like the size of a human hair. So the current we put through there is very small before it burns up. Okay? Now, I didn't push that button yet. So I'm thinking something's going on here. Alright, so what I'm going to do is I'm going to stop the simulation, and terminal 1B, terminal 1A, I'm going to rotate this well, it won't fit over there now, will it? Alright, so I'll rotate it back. And put it back in there. Let's move it so that we've got this terminal 1A, 1B. I think that's what we had to start with. Alright, so let's scoot it back. Start simulation. Alright. So as of right now, for some reason the button is not working. Alright, so we'll delete that button, start the simulation. There's no current flowing because that button's not there. I don't know why the button's shorted. We're going to try another button. Let me right click it. Like, there are two types of buttons really, and there's a normally open button, which means that current doesn't flow because the gap is open. And there's what's called normally closed, where current flows because the gap is closed until you push the button. So normally open lets current flow when you push it. A normally closed kills current when you push it. Okay? Now, these aren't normally closed. Okay? So, we're going to have to, play around with it for a bit. What we're going to do is, we're going to try the simulation one more time. Still nothing. Let's move this right here. Start simulation. Still nothing. Alright. Let's see what happens when we add a resistor. We already know that it's telling us that there's too much current for that LED. So after we push that button, it would have blown anyway. we're going to put a resistor in here, and what a resistor will do is limit that current, okay? Now, the more resistance you have, the dimmer the LED is. So a lot of times it's a play-off between wanting as much brightness and not blowing it. So most red LEDs are, capable of drawing 20 milliamps without blowing. Well, without any resistance, 9 volts divided by 0 ohms, when you divide by 0, that's, an asymptote toward infinity. Okay, so you're getting as much current as that battery can handle. So what we'll do is we'll start with a small resistor. Okay, so we're going to take this resistor over here, and we're going to put it in here so that it's connected here. We've got 1 kilo ohm. Let's go ahead and put it, at 1 kilo ohm. That's 1,000 ohms. We're going to start that simulation. We got the LED coming on at the whole time, so I'm not completely sure how they've got this pin out. Usually it would jump between those 2 pins. Let's see if it's going to jump across these 2 pins. Okay. Now we don't have a gap there, so what we're going to do is we're going to move this wire, or put a new wire in there. That's going to connect to this terminal. Okay. So we're going to go from red to here. We're going to make sure it's red. And terminal 1B and terminal 1A might be electrically connected. And then when you push that button, those 2 terminals are connected to those 2 terminals. We'll find out in a second. Okay, so not pushing the button, the LED is off. Let's go over here, push the button, we got the LED. Okay, now it's pretty dim, like 20 milliamps. So we got 9 volts, divide by 20 milliamps at 0.02. We're well below that 20 milliamps. Would need about, let's say 300 to 400 ohms. Well, I can't do the math right now, but let's go and put 1 ohm. All right, so we've got a little omega symbol here, and that represents ohms for the resistance level. If we push this button, we're going to pop that LED. Okay, and if we still hold down and drag down there, current through the LED is 808 milliamps, while absolute maximum is 20 milliamps. So what we're going to do is we're going to play with this for a second. We're going to put 100 ohms. We're going to push this button. Now it lit up, but it gives us a little information bubble. And what the information bubble is going to tell us is, hey, this amount of current is probably not enough to blow it right out, but you're going to have significant heating, which is going to wear it out pretty soon. Okay, so let's go see what it says. Well, current through the LED is 65 milliamps. Recommended is 20 milliamps. Usable lifetime of the LED may be affected. It will at 65. So if we go up to 200, we should get it down to about 32 milliamps, right? Everything being proportional. All right, so if we double that, the current should go down by half, right? Okay, so 33.8. So they're not saying that 9 volt has a pure 9 volts on it. Or I'm doing my math in my mind wrong. So let's figure out what resistance we need for that LED to be right around 20 milliamps so we can get the most out of it without blowing it. All right, so we're still, we're at 22.9. So I wasn't far off. So 300 was still too little resistance and I was letting too much current go through. 400 didn't blow it, didn't give us a oops thing. Let's try that 350. All right, so we're right in there with getting the LED as bright as we can. Okay. So what I need you to do is I need you to look at this circuit, build it, and either film on your phone, screenshot, or do something to be able to upload that you did this. Okay. Now, doing it exactly like me isn't hard, but you got to realize that, like, if you did this and then your friend asked, and like I see, the same circuit over and over again, I'm going to have questions. I'm not doing this to give you busy work. I want you to get used to it because these circuits are going to get bigger. Okay, so do it yourself. If you have any questions, you can ask me or Ashley. But this'll get us, pretty far on our trek of getting some labs done. Okay, we're about to start learning about diodes. An LED is a diode that has a specific function. Like whenever it conducts, it emits photons, and we like that. Like we can use it for indication and illumination. So the stuff that we're about to start learning about diodes is going to be pretty interesting and pretty useful. Okay, so this is just one example, but we got to turn the LED on. Later on, when we do have like physical labs toward the end of the semester, we'll rebuild this so that you can actually play with the breadboard. All right, so what I want you to do is after you get done doing this and simulating it and making sure that everything is all right, I want you to screen record. You can get, OBS. You can film it with your phone, or you can take a screenshot. Okay, the way you take a screenshot on a Windows is the snipping tool is a little Windows button, Shift plus S, and then your screen will go black, and you'll get a little cursor. And you can drag over whatever part of the screen that you want to take a picture of. Then all of a sudden, a little pop-up will say, you've got a screenshot, and if you click that, it'll let you save it. And then you just save it somewhere you can find it, be it, downloads or documents. And then whenever you need to upload it. Don't make, an extremely long video. If you make a video, I just want you showing the circuit working. I appreciate y'all. Hopefully holy moly, this is a 30-minute video. Hopefully these will get down to about 10 minutes, but I'll continue working on that. So I hope y'all have a good one. Let me know if you have any problems.